So let's talk about 2A. First of all, we will have to try to sketch the region of integration, right? So to do that, right, so we consider the integration limits. So the integration limits gives us four lines, right? So they are y equals 1, y equals 0, so x equals 1, and x equals square root of y. So then of course, the integration limit is the region bounded by these four lines, right? So this is the region that we are considering. So first of all, if you just look at this inner integral, right? So you realize that you cannot find the answer, right, analytically, right? So this integral cannot be expressed as some elementary functions. So now let's try to reverse the order of integration, right? So if we follow this dx dy order, right, so what we are doing is cutting the region like this, right? But what we want to do is the other way around, right? So we want to cut the region this way. So then we write down the integral like this form. For y, right? So that means we are considering a particular small bar here, right? So I want to first find out the lower limit and this upper limit. So the lower limit is always 0. And then for upper limit, right? So at a particular value of x, right? So y is equal to x squared. So now for the outer integral. For the outer integral, it's just going from this point, x position of this point, and the x position of this point. So it's just again from 0 to 1. Now, if you try to consider the integral again, you find that it's much easier, because at least for the inner integral, right, when we do it with respect to dy, right, so this one is just a constant. So that means it's equals to this. Right, just integrating this gives us x squared. So when you see this x squared dx, right, so you know that you can do a substitution of variable. Like we let u equals x cubed, right? So then du would be 3x squared dx. So that's why this integral can be written as so then this is something that you can exactly integrate. Okay, so now let's try the part B. Okay, part B. Okay, let me just draw it here. So again, I have 4 lines, right? So just y equals 1, y equals 0 again, and then x equals 1, and then x equals y. So this is the region. So now again, if we follow this order, right? So if we just look at this inner integral, again, you find that you cannot do it analytically. So what we are going to do again is to reverse the order. So go with dy first. So that means again we are cutting the region like this. So in that case, again we consider a particular value of x, right? So then I consider this y position and this y position. Y always go from 0. And then because this x equals y, right? So this is x. And then again, for the outer integral, start from here and here. So from 0 to 1. So again, you see that this integral is much easier now, because again, when we do the inner integral, this exponential function is just this e to the power x squared just can be taken outside, right? Because this is just a constant when we do the inner integral. So then what we have left is this. So again, with this, you know that you're going to do a substitution, right? So let x, let u equals x squared. Then du is 2x dx. So then your integrals becomes like this. Okay, so one more small remark is that you see that for part A, when I do the substitution, and then also for this part B, when I do the substitution, I did not mention anything about the limit, right? And of course, in this case, it just so happened that the limit don't have to be changed, right? Because when x is 0, u is 0, right? And then when x is 1, right, 1 squared is also 1. But similarly here, when x is 0, u is 0. And when x is 1, 1 cube is also 1. So that's why I did not need to worry about the changing of limit here. But you understand that in general, you should pay attention to whether you need to change the limit. So this is the end of the tutorial. Well, the first two tutorial problem. Okay, so we'll go back to the lecture notes for some time, and then we'll go to the third tutorial problem. So in the last lecture, we have started to talk about the triple integral, right? So now we have a function of 3 variables, right? And then I want to integrate this function over a 3-dimensional this box region. Right, so I mentioned last time that it's difficult to actually draw a 3-dimensional function. Right, so but one example, as I said earlier, is that you could imagine that you have a room, and then you are considering at each point of the room where you have a temperature. Right, so and suppose there is some kind of temperature variation, right, across this region, right? So then you have some part of the room colder, and then some part of the room hotter, right? So then you can basically express this temperature distribution, right? So as a 3-dimensional function. So and you may still remember that, for example, here, right, one way to represent the 3-dimensional function is using this color, right? So if I use this red, right, to represent the hotter region, right, and then this blue to represent the cold region, right? So there's one way that you can visualize the function of 3 variables. So and last time when we do the integration, right? So when we do the integration, we are considering a box region, right? So either it's a cube or like a rectangular box. So basically, in this case, right? So all the integration limits can be expressed by constant only, right? Because basically we are talking about a box region can be considered as the region bounded by 6 flat constant plane, right? 2 for the x direction, 2 for the y direction, and 2 for the z directions. So that's why we have all these constant limits. So today we are going to talk about a case where the region has an irregular shape. Okay. So you see that this is the original figure that I have in the lecture notes, but I realize it's not a very good one. So here I make a new one. Okay. So I'll update the lecture notes on Blackboard. Okay. So what I'm considering here is that suppose again I have this 3-dimensional space. Okay, this 3-dimensional space. I forgot to add the label the axis, x, y, z. So then I have some function of 3 variables, right? So and we don't worry about what that is, but suppose I want to consider an integration region, right? So this integration region looks something like this. So what do I have again is what do I have again? 6 surface, but not 6 flat plane. Okay, so so we need to be very careful here. Okay, so just follow it carefully. Is that I have the up and the down surfaces, and then this red one, the front, and then the back, or the other red one, front and back, and then 2 black one, the left and right. I have 6 surfaces, and then all 6 of them were again enclosed a region, right? So I want my integration region is called D, right, which is the region enclosed by all these 6 surfaces. So here, so let's go with the easy pairs first. Is that the front and the back? Okay, the red one are still 2 flat planes. Okay, suppose. So x equals A, x equals B. Just 2 flat planes, right, parallel to the YZ plane. So next, I have the left and right, right? So the 2 black ones. So they are curved. Okay, they're curved. So the one on the left, I use a function to represent alpha 1x, alpha 2x. Okay, but notice that they are not functions of they are only function of x. Okay, so they are not function of y. They are not function of z. Okay, well, of course they are not function of y because y is the subject term here. So they are not function of z. So what it means is that, okay, it can be curved like this, right? But still, whenever you cut the plane like this, right? The line that you see is always a vertical line, right? So let me try to make a picture here. That means this kind of plane cannot be a plane that looks like this. Okay, because for this one, it has a z dependence. Okay, I can have this kind of plane. So as I said, if you cut it like this, and then you look at the edge, then you find a vertical line only. Okay, but here it is different. If I try to cut this plane, right, then I will see a curved line. Okay, so I have this kind of plane, not this kind of plane. Okay, finally, the up and the down. So these two are the most complicated ones. Okay, they are function of the both x and y. Okay, so it can be curved in both directions. So now to find out this triple integral, okay, we can express it like this. So here I have a particular order, right? dz, dy, dx. So that means I'm considering the integration over the z direction first. So that means I'm going to consider a line like this first, right? So the upper edge, the upper point, the upper end of this line, right, would be a point, right, on this upper green surface. And then the lower end of this line, this vertical line, would be a point on this lower green surface. So when we do this integration over this line, right, so then this will be my lower limit, this will be my upper limit. So of course, the z position of this lower limit, or the z position of of this lower point, will be given by this function, right? And then the z position of this upper point will be given by this function here, right? So that means if we pick a particular xy position, right? So then the z position of this point is known, right? So the upper point, of course, you have to have the same xy position as the lower point. Then the z position given by this. So that's why I have this as a lower limit and this as the upper limit. So now I'm going to integrate along the y direction. So that means I have this done, and then I'm going to consider this entire plane here, right? So going along the y direction. So the limit, right? So I need to, of course, is that my blue plane, right, will intersect with this black surface on the left. Right here. Here. And then the right edge, right, will be here. So that's why I need to know the y position of this point, right? And also I need to know the y position of this point. So the y position of this point, right, is given by this, right? So you pick a particular value of x, right? And the y position is alpha 1 x. And then here, you have a particular value of x, and then your y position here is alpha 2 x. So that's why for the y integral, my lower limit is alpha 1 x, upper limit is alpha 2 x. So now the last part, after I have this plane done already, then I need to consider all the plane, right? So this is one, right? This is the other one back there, and then the third one, even going back more, right? So I'm stacking many planes, right, to fill up this entire space, right? And that's why, right, the first plane, right, will be the plane that touching this x equals a plane, and then the last plane will be the one that up front touching this plane x equals b. So that's why my lower limit is a and my upper limit, right, is b.